Time for us to tackle and then master link state protocol concepts and OSPF in particular. We're going to lead off with a little bit of theory, of course, and it's link state protocols that we're discussing as a whole first. And the two main link state protocols out there today, OSPF being one and IS to IS, intermediate system to intermediate system, being the other. But IS to IS is not a CCNA exam topic. And then we've got one lab after another and a lot of detail. This is probably the most detailed section in the course as far as the lab work goes. So a lot to do here, so let's go ahead and jump in. We've talked about this with distance vector protocols before, that their transmission of full routing tables far too often. Frankly, it's just totally inefficient. It takes up our bandwidth. It's going to hit the router CPU. And the thing is, with RIP packets in particular, those packets are limited to 25 routes. So if you had 51 RIP routes that a router needed to advertise, it would send out 3 packets every 30 seconds advertising the same freaking routes. And it's just a tremendous waste. Now, that's one big difference, as we're going to see in a moment here with with link state protocols, because link state protocols don't do that. Now, another major difference is the format of the update itself. Now, at the end of the static routing section, I did run a RIP debug, or showed you the output of one, and we saw that the routes and the metrics themselves were right there. They didn't have to be interpreted. They were right there in front of us. Well, link state protocols do not exchange routes and metrics like that. Link state protocols exchange just that, the state of their links. And there's a cost associated with those links. OSPF refers to its metric as cost, and that's a term that we will definitely revisit because on occasion you want to tweak your OSPF costs. But right now it's just enough to know that that's how OSPF refers to its metric. Now those LSAs, the link state advertisements, as they arrive from OSPF neighbors, the router places them into a link state database, a database that's going to be just a little more complex than that username password database we made earlier. The good news is, even though the database freaks people out at first, and I don't know any other way to put it, the first time you look at an OSPF database, like, oh my gosh, what is all that stuff? Well, you really don't have to worry too much about what the individual entries are, because the Dijkstra algorithm is going to take care of it. It's going to run against the contents of that database, and it's going to give us a routing table, much like the one we're already familiar with from our static routing work. Now, we need to know what these types are that they're mentioning here, like router link states, net link states, summary net link states, and I have plenty of information for you that later in this part of the course. And this is the command show IP OSPF database. And frankly, production or lab, if OSPF's working beautifully for you, you can go a long time without looking at the database. It's not something you're going to do every single day or anything like that. But we need to know our way around it just a bit. And this is a very small database for OSPF. Usually it freaks people out when they see a production one first and it's just one screen after another, or just 30 links, 40 links or more, where you're seeing 1 or 2 here. But don't let it freak you out. Now, technically, this is a routing table, but again, the algorithm does the dirty work for us, gives us a routing table that we can interpret much more easily. Now, this exchange of LSAs between neighbors in OSPF really helps bring about one major advantage of link state protocols. All routers in the network are going to have a similar view of the overall network. Now, we may not want that. Let's say if a router has 50 routes in its table and the next hop router is always the same router, we might want to do a little something about that, and we'll talk and do that in a lab later in the course. But the key here is, by default, all of our routers are going to have a like view of the network. Now, before the LSA flooding, I definitely want to mention that. Each LSA is refreshed every 30 minutes. That is on an individual per LSA basis. I don't want anybody thinking, well, twice an hour, every LSA in my network is going to be refreshed all at one time. That would be a lot of work for our routers, and we would not want that. So again, the LSAs are flooded every 30 minutes, but each one has its own little timer. And now they're also flooded when there's an actual change in the network. But again, that refreshing is every 30 minutes, and it's on a per LSA basis. Before any of this can happen, though, we've got to form a neighbor relationship with the downstream router, and that's an adjacency. Neighbors have to be discovered, and then you form an adjacency with that neighbor, after which the LSAs are then exchanged. Now, more about that after we discuss the designated router, the backup designated router, and just a few things that can mess up our adjacencies as well. And about the DR and BDR, a vital concept here about OSPF, because we're always interested in keeping our overall overhead down. Everything's got a cost that we're doing. And if all routers in an OSPF network had to form adjacencies with every other router in the OSPF network and then continue to exchange LSAs with every other router in the network, wow. I mean, just a huge workload, a ton of bandwidth being used, and anytime a router flooded a change, it would just be horrendous. You'd have basically, a network full of routers all screaming at each other at the same time. And not only would that not sound good, it would be not only an inefficient design, but it's just a huge waste of network resources if that happened. But most OSPF segments are going to elect a designated router and a backup designated router to handle network change notifications. Now, when you see the word elect and you're studying for a Cisco exam, there's an election going on. We got to know the rules, and we're going to master those. But first, a note here about that DR. The designated router is actually the router that will receive the LSA regarding the network change from the router that detected the change. It's then the DR that floods the LSA indicating that change to all the non-DR and non-BDR routers. So it's done in a much more orderly fashion than, say, everybody just screaming at everybody. The router that detects it lets the DR know about it, and then the DR lets everybody else know about it. The router that detects that change also lets the BDR know about it. The BDR does not announce it. That's the DR's role, but the BDR gets that information at the same time the DR does, so it can have an absolutely up-to-date database in case it has to quickly step in for the designated router. Routers that are neither the DR nor the BDR for a given network segment, they're indicated in Show IP OSPF Neighbors as DR Others. And you will see that very shortly. We're going to be checking a lot of adjacencies. Now again, instead of having every router flood the network with LSAs after a network change, the DR Other that detects it, or whoever detects it, sends the update to 224.0.0.6. And that is the all designated routers multicast group. And the DR and the BDR naturally are members of that group, so they are listening to 224.0.0.6. They hear it and go, hey, okay, I just heard about this change. The BDR will update its database, but it will not make an announcement. But the DR will then flood the change to 224.0.0.5, the same address to which our OSPF hello packets are sent. No coincidence there, because every OSPF speaking router is listening to 224.0.0.5. And that's how the news of the change gets flooded out in a very orderly fashion. Now again, the DR, the backup designated router, it's the backup. It's just waiting, and if the DR goes down, tears an ACL, whatever, they carry the DR off and the BDR steps in. The BDR is promoted to DR, and then another election is held, and that one's to elect a new BDR. And that's why the network changes, again, are sent directly to the DR and the BDR on 224.0.0.6, because that way the BDR is ready to step into the DR role at a moment's notice. The backup quarterback always has to be ready to go in. Now, just a quick word about the Dijkstra algorithm here. There's an argument, well, does OSPF, recover quicker from a network problem than EIGRP does? Well, I'm not going to get into that argument here, actually, but the Dijkstra algorithm, the SPF algorithm, it recalculates network changes so quickly that routing loops literally don't have time to form. It's an amazing thing. And with EIGRP, as you're going to see, if you haven't looked at that section yet, the backup routes are actually calculated in advance of them being needed. So if the primary route to a destination goes out, bing, we've got a backup route in there ready to go in and play. Now let's talk about those hello packets I mentioned there for a moment. Hello packets perform two main tasks in OSPF, and as anything called a heartbeat would be, they are both very vital. OSPF hellos allow neighbors to dynamically discover each other, and they allow the neighbors to remind each other that they're still there, which means they're still neighbors. Because as with really all of our protocols, both layer 2 and layer 3, once we make some kind of adjacency, it's not permanent. You know, we've got to keep refreshing the adjacency, if you will, and that's what our hello packets are all about. Now, our OSPF enabled interfaces are going to send hellos at regularly scheduled intervals. The default intervals are 10 seconds on a broadcast segment, such as Ethernet, and 30 seconds for non-broadcast links, such as a serial link in an NBMA network, which is what we're going to configure. We're going to configure a lot of OSPF networks in these labs, and you'll see those hello and dead timers come into play here shortly. The OSPF hellos again go to 224.0.0.5, and we know that's an address from the reserved Class D range of multicast addresses. Now, OSPF neighbor relationships are really just like relationships between people. You know, we know that just because somebody moves in next door and says, "Hi there," you know, it doesn't mean that we're going to be really neighbors. You know, maybe they play the music too loud, we have noisy parties, don't mow their lawn, park cars on the front yard, I don't know, you know, whatever works or doesn't work. But, you know, you can have a disagreement on one of these things that you think is important, and then you're not really neighbors. Well, OSPF routers are kind of like that because they have to agree on some important values before they actually become neighbors. And I'm going to show you these values now, and we're going to see them live as well. And I would definitely have these down cold for the exam in the real world because, frankly, most OSPF adjacency troubleshooting, almost all of it really, it's simple. It's nothing incredibly complex. You just have to know where to look for the information and what has to match and what doesn't. And we're going to see all this live in about 30 seconds actually. Now what we're going to do here is assume an Ethernet link, or actually I'm going to go ahead and set this up actually. I want you to see this live. I don't want to just go through it in the book here. We're going to have an Ethernet link between a couple of routers, and they're going to have to agree on some values, and one of those values they're going to have to agree on is the subnet number and mask. I apologize, I know those routers are very small, but I will give you the IP addresses there. They're 172.12.23.2 and 172.12.23.3, but they have slightly different subnet masks. One has a /24 and one has a /25. We will pick up there and see what our adjacency situation is there on the very next video. See you there.